So for about like the past like semester and a half, we've been working on studying the cooling mechanisms of primordial stars. And specifically, we've been looking at comparing a novel mechanism using the H3 plus Rydberg molecule versus a existing mechanism that's using H2 and HD and like other existing established stuff.
This is Gokul.
Oh yeah, I'm Gokul.
I'm Jeremy.
Anthony. We're all sophomores.
So back at the very beginning of the universe, we have the Big Bang, and then a bunch of quantum fluctuations, and eventually our atoms and molecules will start to form. And then at some point, like about some tens of millions to hundreds of millions of years in, we get this massive cloud of gas and dust, right? About 400 million years in, we get stars start to form. Now, the key thing here is that for these first stars to form, a lot of things kind of had to line up. The universe had this like gas and dust were going to cool down. PV equals nRT, right? To get a higher density, you'd have to cool down the dense mass. So, understanding this mechanism, these first stars forming, and this like density change, this like local density change in certain areas of this gas and dust, is a really attractive problem to us. It's a really interesting problem. So, what we see today are two distinct populations of stars, right? It's been defined as population 1 stars versus population 2 stars. Population 1 stars are those with about 1 to 3% and higher of metals. And population 2 stars have about 0.5 to 0.8 to 1% metals. The reason this is really important is because the presence of any sort of metals, of any small amount of metals, can drastically influence how a star forms and acts. So as you can see, this is a plot of theoretical cooling efficiencies versus the metal content. So we can see that overall, at throughout the entire temperature range, we see a significant increase in the cooling rate, even with as we increase metals slightly, the metal content slightly. So
what metals are you referring to?
Oh, sorry, just to clarify this. When we talk about metals, we mean anything heavier than helium. So the chief coolants in population 1 and 2 stars are lithium, beryllium, carbon, oxygen, iron, right? So those are kind of the driving forces here. They're not like real metals, they're just everything that's not hydrogen. So we established that in today's stars, we've got these heavier elements are the primary coolants. And actually one thing to note right here is at about 10 to the 4th Kelvin, we see a drastic drop in the cooling efficiency. I'll get to that in just a minute. That's something particularly important to know.
Go back, what's the y-axis?
The y-axis is the cooling rate.
Higher means?
Higher means each molecule can cool, it has a higher cooling rate. So this is cooling rate normalized to number density. So given that today's stars have metals, we can, in about 2004 through 2006, an entirely new population of stars was proposed. Those of population 3 stars, because at the very beginning of the universe, just after the first atoms and molecules, atoms had started to form, we don't have anything heavier than helium, right? The only elements present are hydrogen and helium. Now, given that metals are actually the most efficient cooling mechanism we see today, if we remove everything how current stars form, how is it possible for the very first stars to form? And we know that they did, considering we can still see background radiation from them, right? After these population 3 stars would have formed, they would have been able to release ionizing energy to form other stars, but the very first ones are still kind of a mystery. Now, to understand this, we have to start by looking at the temperature of the universe, right? From the very beginning, right after the Big Bang, we've got some 10 to the 31st Kelvin, but that cools down to some 10 to the 9th Kelvin once the primordial clouds of gas and dust have formed, right? Before the formation of the first stars. Now, for these stars to condense, we'd need about some 10 to 100 Kelvin. Somewhere within that range is what we'd expect. Now, for that to cool, it's it's a pretty difficult question. I mean, from up until 10 to the 9th Kelvin, we can get like a lot of atomic cooling mechanisms. But at 10 to the 9th Kelvin, we start to get charge interactions and molecular interactions. They start to come into play. So this initial cooling, this first step from 10 to the 9th Kelvin to 10 to the 4th Kelvin, is mediated by Bremsstrahlung radiation, or atomic cooling. When two charged particles come near each other, they repel and release electromagnetic radiation, carrying away energy. This is very much favored up until 10 to the 4th Kelvin. So we've got an efficient cooling mechanism. Now, if you remember earlier, at 10 to the 4th Kelvin, there's that drastic drop in the cooling efficiency. That is partly a function of this, right, of Bremsstrahlung radiation becoming unfavored at 10 to the 4th Kelvin, around that temperature. Now, what we also expect is that these very first stars would have formed in what are called mini halos. So as energy is radiated away, you get areas of higher density and lower temperature, and other areas of high temperature around them, like a ring of high temperature around that. And these mini halos would have further facilitated star formation. They would have created background radiation, ionizing radiation, and they would have created a pressure gradient. So we kind of expect these stars to form in clumps, right, surrounded by these so-called mini halos. Now, this leaves us an open question. After 10 to the 4th Kelvin, below 10 to the 4th Kelvin, how did these stars begin to cool? Because, I mean, we don't have metals, and we don't have any charge-based repulsion. We don't have like the same level of charge-based repulsion and electromagnetic radiation-based cooling. So below this temperature, we've got a few different theories that are out, and each has their own merits, but the major one is via H2, the H2 and HD molecules.
Right, and so like we said earlier, the early universe had abundant hydrogen. So the proposed theory that, or the generally accepted theory of how like a cooling mechanism below 10 to the 4th was 10 to the 4th Kelvin was that you have this associative detachment of a hydrogen atom and a negatively charged hydrogen anion, both high in translational energy. They collide with each other, and that kinetic energy is stored into internal energy. And when it's stored into this, when it's excited, that energy can slowly be radiated off, and so you dispel energy overall in that system, and so you get an overall cooling. Yeah, and so the earliest, most studies that looked into this mechanism tried to come up with a rate coefficient to determine exactly how fast, exactly like how this, like to characterize this mechanism, but most papers couldn't seem to agree on a it's like one rate coefficient. And
yeah, so we see, in addition to H2 cooling, we actually see the HD molecule is actually like a couple orders of magnitude better at cooling than H2 is, especially at low temperatures. Reason being, it's asymmetric, it's got a dipole moment, so that's part of what drives this more efficient cooling mechanism. So, looking at kind of the critical mass of HD needed to cool these mini halos, we need a number density greater than about 10 to the -6th for this HD cooling mechanism to be effective. And when we look at it, especially in these mini halos, we see a lower number density than 10 to the 6th, like below the critical number density for the critical mass for stars to collapse and form. Now, in other areas, we've got a sufficient number density. That's enough for like full galaxies to form and for supermassive black holes. But in the areas we're interested in, with the very first stars, we don't hit that.
Question. Say, do you guys know what the ratio for hydrogen to deuterium is in the early universe?
I can't remember it off the top of my head, but I know deuterium formation is very heavily favored. Do you guys actually remember?
I want to say it's anywhere from like 10 to the -3 to 10 to the -5, D to H, but with even if it's like a really low ratio, the kind of this HD mechanism dominates over the HH1, and so it's able to.
So we're able to
still
approximate. Yeah. So.
Yeah. So this is just a single figure that kind of compiles most of a lot of different studies and their how they try to calculate the rate coefficients and at varying temperatures. And basically, like, the point of this figure was to show that there's not a lot of consensus as to what exactly this rate coefficient is. They differ by like 2 or 3 times. And the explanation that this paper discussed as to why there's such a big discrepancy is that there's a lot of different. So they try to determine rate coefficient. They're examining the rate of destruction of H minus, and so this paper was suggesting that because H minus actually goes through a lot of different, has a bunch of different other pathways it could go through, and the paper said that the paper simplified it down to only 28 reactions, but not all of them result in like this cooling mechanism. So they were saying that because there's so many different pathways, it's hard. Like, they don't really know what the metrics were for these other papers of how they're exactly measuring the rate coefficient, and so you get this band, this spread.
So on top of that, we've also got a few other things that are preventing this H2 cooling mechanism from dominating. We see this background radiation, this Lyman-Werner photon-like radiation, emits photons. Like, we see all these free photons, these free background photons, varying by the number of excited molecules in an area. And naturally, in these mini halos, we tend to see a high background. We tend to see a high background Lyman-Werner radiation. Now, we can kind of estimate the minimum radiation necessary to like heavily limit cooling by comparing the formation time of H2 and versus the photodissociation time at a certain photon concentration or photon flux. So what we see is actually as we increase down there the flux of the Lyman-Werner photons, a small increase any increase heavily increases the critical mass necessary for the star to collapse, right? So if you've got more photons, you can add a larger mass of gas and dust can collapse into a star. Now the thing with this is we actually see supermassive black holes and supermassive stars, like some 5 orders, like 10 to the 5th the size of our sun, if this holds, right? So especially in these mini halos. Now this is okay again for the rest of the universe where we get later on galaxies, right? But with the first stars, considering Lyman-Werner radiation, is much higher than the critical to prevent reasonable star formation. This is another thing that's kind of holding back and limiting the H2 cooling mechanism from dominating.
So what are we seeing on this plot? Is this data points in a model that's trying to fit to it, or is this like a boundary?
This is these are theoretical data points. So they calculated the critical mass for collapse versus the photon flux.
Okay, and what's the dashed line?
The dashed line.
Is that the theoretical?
I actually don't remember that off the top of my head. Sorry. The main focus is the heavy ones. I can get back to you on that.
And so because there's been a lot of things that go against saying H2 as a efficient mechanism. The Stickley group Stickley and a few astronomers, they were trying to figure out different, maybe suggesting a different mechanism. And so the proposed mechanism was this H3 plus triatomic positively charged hydrogen ion molecule, and it's dissociative recombination with an electron. And so this is the overall scheme, and these two on the top, they're just binary two particles colliding with each other, and then they form these neutral products. And then the third one is a ternary reaction, which, as we know, like they're pretty uncommon, but or yeah, more on that later. But they've also been, it's been generally accepted that the in between these steps, it goes through a really high energy H3 Rydberg intermediate. And so before we move on, I'd like to talk about like a brief history of all the studies of H3 plus. So H3 plus dissociative recombination has, it seems simple, but there's been a lot of problems surrounding it. And so to begin with, similar to the H2 mechanism, the H2 cooling mechanism, there was a lot of discrepancies with the rate coefficients and figuring out exactly how fast this recombination was occurring. And so it was, so like going back a little more, it was first discovered by J.J. Thomson in 1911 when he was doing an early form of mass spec on plasma, and he discovered a molecular ion with a mass to charge ratio of 3. So he could either assign this to carbon 4+ or hydrogen triply bonded and positively charged. And so when he increased the hydrogen concentrations, this peak went up a lot. So he determined it was this H3+ molecule, and ever since then, a lot more studies have been trying to look into this. Eventually they found this H3+ molecule is very abundant in interstellar media, and so a lot of astrophysical implications could be drawn from the studies looking into this. And so most of the papers the early papers, they'll describe either direct or indirect mechanism. And so the direct mechanism is just the recombination happens one step and then you get your product. And then the indirect mechanism has a first step is forming this H3, so the neutral H3 Rydberg molecule, which is a really high, very high energy metastable molecule. And multiple theory papers have proven that this indirect mechanism is what actually happens. And so yeah, and so more issues with just in general with studying H3+ dissociative recombination. Because this is a triatomic system, the vibrational degrees of freedom have 3 dimensions, and so it's more complicated than just diatomics with fewer dimensions, and for degrees of freedom. And these are 3 vibrational modes for H3+. And so the first one, you just have all of them stretch away from each other, and it's termed breathing because it kind of resembles like an animal breathing. The second and the third one involve bending as well. So into and out, like with respect to each other, it's like into and out of. And yeah, more on that later. And
do you have frequencies for when these should show up? Does that come later, maybe?
Yeah, I think so. But yeah, anyways, and then some other issues, some general issues. So the two most common types of experiments with H3+ recombination is what were called plasma afterglow experiments, and then storage ring experiments. And so these two, the different types of experiments generated 2 different rate coefficients, and they differed by order of magnitude. So there was generally no consensus as to why, or no explanation as to why these 2 values were obtained. And that was until 2001. Gokul and Green, they proposed a model which incorporated the John Teller symmetry distortion effect, which basically just states like if you have degeneracy and you have a geometric distortion, then the degeneracy will the energy levels will split, and because like the very nature of this involves the molecule distorting geometrically, they incorporated this this distortion effect into their model, which they also described that like previous studies have never done this, and so when they used their model and they obtained their values, they pretty much closely matched with experimentation. So these are the values for the branching ratio. So like how much of this product. So the other product would be like H2 and plus. It was like a few slides ago, and then this one's just the 3 neutral hydrogen atoms. And so the values that they obtained for the branch ratio for their model was 0.7 and plus or minus 0.07, and then as you can see, it pretty closely matched with experimental. And then these were, they also mentioned that the rate coefficient that they obtained, even though this was a plasma afterglow experiment, was the data they obtained was also like around 10 to the minus 7 range for the rate coefficient, which this one, Jensen et al., this is a storage ring experiment, which is usually those two would usually have differing rate coefficients, but after incorporating this John Teller effect, they were able to match with the storage ring experiments.
Can you briefly talk about what a storage ring experiment is?
Yeah, so you have these, basically it's like a circular ring, like, and then you have ions that are flowing like through it, and they go, actually wait, Anthony.
Yeah, so instead of, so in the afterglow experiments, that's pretty much, you're creating a plasma and you're gonna be trying to recreate the conditions in the early universe to where you would find and hopefully see these types of reactions happening. Whereas the ion storage ring experiments, you're kind of forcing these reactions to happen. You're creating a collision. So you're storing your ions, you're accelerating them, and so in this case, we would have our H3 plus ion and be like manually colliding that with an electron. So following, so in the 80s and the 90s, the astronomist equipment was catching up with spectroscopist equipment, and so they were actually able to find and see H3 plus out in the universe. Meanwhile, there were still discrepancies in these in-lab calculated experimental recombination coefficient rates. And so at the turn of the century, there was a big push to settle these discrepancies and find out what conditions are we not considering, where are these arising from. And so with Fonseca dos Santos and University of Central Florida, she was able to, her theory was able to calculate that H3 plus isn't just one, it's not just one chemical that we're looking at, it's essentially two different chemicals, and that arises from its different like fermion nuclear spin states. And so we have para H3 plus cation, and then we have an ortho H3 plus cation, and she was able to calculate that the para H3 plus, when it collides with an electron and recombines, that its intermediate is a lot more stable than that of the ortho H3 plus, and so it's able to maybe go through further reactions that this other portion of H3 plus wouldn't. And then additionally, in this excited state of this collided para H3 plus, its cross section is bigger, so making it more reactive. And as Glossick will try to seek out, that because of this bigger cross section, that it's able to have a ternary collision with a two-step process. And with these para and ortho H3 plus cations, Pictronini in 2009 points out that some discrepancies come from other experiments not taking into account the internal temperature of the molecules that they're looking at. Next slide. And so for these H3 plus nuclear spin states, we have para where it's 2 up, 1 down, and then ortho is they're all the same going up. And theory has calculated that at lower temperatures, para is more dominant. Meanwhile, ortho is more dominant at higher temperatures. And these red lines these indicate the ortho H3 plus rotational states, while these blue lines are the molecule of interest for the para H3 plus rotational states. Next slide. And furthermore, we're able to, so based on this temperature related concentration of para and ortho H3 plus cations, the McCullough group at the University of Illinois, Sherbana, they describe H5 plus intermediate, where if you have two different, if you have an H3 all ortho molecule, it can collide with a different molecular hydrogen molecule to form these, kind of swap these spin states around, so you can get these para H3 plus cations of interest. Next slide. And so the Glossick group, following this theory, they sought to reproduce it. And this is what they did. They showed that the para H3 plus recombination coefficient rate is a lot higher at lower temperatures, seen with these triangles here. Here are the coefficient rates for recombination. These dotted lines, this blue dotted line is the theory, calculated by Dos Santos. And then you'll see that the ortho H3 plus recombination coefficient rates differ a little bit from theory, and they're a lot smaller as the temperature is lower. Next slide.
Sorry, do they give a reason for that?
So part of the reason is in this excited collision, this excited state from the recombination collision, they describe it as the para H3 plus cation having a bigger cross section, to where it can react faster, and that's how they described it. Does that satisfy?
Yeah, I'm just trying to, so if they know it has a different cross section, that would be something that they could take into account in theory, I would think.
Mm-hmm.
So typically when there's a deviation from experiment, it means there's something wrong with the model, right? So.
Look into it for the next meeting. And so here, and so yeah, so with this higher cross-section para H3 plus cation and it being dominant at lower temperatures, Glossick and his grad student, they go on a quest to describe and prove this ternary cooling mechanism, where instead of just having H3 plus combined with an electron and radial energy to cool, it's actually assisted by either, here they propose helium working in this mechanism to where, so with their, sorry, I got lost in my words. So in this mechanism, this ternary mechanism that they propose, assisted with helium, they describe it as the para H3 plus cation recombines with an electron, and it's at this excited state that is a bit more stable than the ortho H3 plus excited state. And so it's able to, because it has a longer lifetime, it's able to collide with other actors such as helium, which would further produce different reactions. And this is the mechanism that they propose. And then, next slide. And then they later found that that the molecular hydrogen-assisted ternary model is indeed a lot more efficient than the helium one. So with high densities of hydrogen, you'll get a faster ternary, or you'll get a more likely ternary mechanism than with helium-assisted one. Next slide. And then more recently, they reproduced their results using deuterium, and they, for the first time, they were able to not only track D3 and H3 recombination models, but they're able to find the rate coefficients for HD2 and H2D, and they're roughly all the same. They're the same for the binary collision mechanisms, and then they're the same for the ternary mechanisms, regardless of if it's mostly deuterium, mostly hydrogen.
And so that brings us up to like what our group aims to do. So in 2001, there was these lasing lines at the 7 micron region were discovered in an experiment that was didn't have to do with this H3 plus recombination, and those lines were eventually assigned as, or subsequent studies were done just with hydrogen and helium plasmas, and they discovered those same lines at the 7 micron region, and so when they matched it with theoretical data, they found that they assigned these to the 4D to 4P transitions for the H3 Rydberg molecule. This was done by the Sigma group.
And so, yeah, they had, they accidentally found this 1430 line in their water plasma, and then it wasn't supposed to be there, so they sought help from theory to assign it.
I'm pretty experimental on this, because a lot of these lasing lines are very hard to detect, right? There's a very high sensitivity to different experimental conditions. A lot of these lines were just discovered in different plasmas at slightly different conditions. So none of the peaks there are quantitative, like none of the intensities are quantitative. It's just the frequencies.
And so the method that they used was it's a pulsed supersonically expanding plasma, and this pulse means that it'll be it's like an afterglow. It's a plasma afterglow type experiment because you have your plasma that's still existing while the ionization source isn't there anymore, or the source of the discharge, and the detection method is using a optical supercavity and a ring down cavity ring down spectroscopy. And so you have these two ring down mirrors on both sides. This is the slit that the plasma is ejected, or the gas is ejected through, and there's a discharge on the plates that ignite this plasma. And then the lasing lines, or just the light from it is reflected on these mirrors, and then the data is like directed to a monochromator, and the monochromator is manually the monochromator is manually like adjusted to sweep through the range of frequencies, and so it was noted in the papers that use this setup that all the spectral lines that were drawn on there may not be like all that there is, because it was manually done, and so yeah, and then so the cooling mechanism, like where it comes in, is when this it's similar to the H2 mechanism. So you have two particles that have high translational energy, and when they combine, in terms of H3, it forms this H3 Rydberg molecule, and what forms first is this complex that has the electron on a really high energy level, and then it cascades down, and while it's cascading down, it emits out photons, which will radiate off energy. And this was termed like top-down recombination.
So the driving force behind this is, like, one of the main questions we need to ask is, does H3 form enough in these interstellar dust clouds and these primordial gases for this to be a valid cooling mechanism at all? And what we actually find is yes, even at low temperatures, we still get a maintained cooling rate of H3. And actually, if we look at D3, it decreases slightly from about 100 Kelvin to 70 Kelvin, and at 70 Kelvin, it shoots up rapidly. That graph isn't here, but so what this graph is showing is red is the present data, and the rest is just the black is theory, and the blue is previous like experiments and predictions in like other models. So this supports the previously mentioned model because we can maintain formation rates. So therefore, I mean, it's possible for this model to occur at low temperatures.
Where's the data from?
As in it's from experimental modeling of it's from both experimental and theoretical modeling of the cooling rate or of the formation rate.
Is this from one of the Prague experiments?
No, this isn't from the Prague experiments. This was a 2018 paper. Yeah, so we can see also that if we look at currently in existing interstellar dust clouds, we see a similar formation rate or presence of H3 in both dense dust clouds at the top and diffuse dust clouds at the bottom. What this shows, this is interesting because that kind of implies that the formation of H3 plus is not dependent on the initial density at all. like on the existing density of the dust cloud?
So in interstellar gas, this is how H3 plus forms. So you have a cosmic ray that ejects an electron. So a cosmic ray could either be a proton or electron, and it ejects an electron from molecular hydrogen. And then that cation of this electron, this molecular hydrogen and the lost electron collides with another neutral molecular hydrogen, and it forms this H3 plus, and you get a neutral atomic hydrogen, and this is exothermic reaction, so it's favored, and it happens a lot, and so this is kind of why, this is the background of why it's so abundant. It's a very reactive molecule, so it's going to go away quickly, but it's formed a lot. And today, the current, so here's like a little more on the history. So in the 80s, they were able to detect H3 plus in the Ianos, the outside of Jupiter, and this was quickly followed by detecting it in Uranus and then Saturn. And then from here, the equipment wasn't so good until we had these infrared arrays that were able to detect for the first time H3 plus in gas clouds. And then the next year, they were able to detect it in the center of our galaxy.
Yeah, so this this detection of H3, the like similarity between the similarity in column density between like diffuse and and dense dust clouds has actually been used to explain like multiple things to date. Like the cosmic ray flux from Zeta Persei was a 2003 letters paper from the Zeta group.
And then one thing that's they found that's really interesting and useful is that that H3 plus, its number density it's not linearly related to the number density of hydrogen, and so so what they've seen is that at high densities of atomic hydrogen, you have high densities of molecular hydrogen, and then also this is able to allow for the formation of CO, and similarly other common interstellar molecules are related linearly to the number density of hydrogen. Meanwhile, H3 plus is found to not be linearly related, and so I think it's on the next slide. Because of this peculiarity, we're able to use this kind of constant column density of H3 plus to, astronomers use it to help determine gas column dimensions, and so like how long they are, and so the way they do that is because the para H3 plus is a lot more reactive, they look for the ortho H3 plus collision with another body, and so because para H3 plus is a lot more reactive, and you won't they prioritize looking at the ortho H3 plus, and we haven't taken PChem yet, but with these ortho H3 plus rotational states, they describe this elevated ortho H3 plus state not being able to radiate off energy to further cool, it must collide with something, typically helium or molecular hydrogen, and then so they use this fact that to get rid of this high state ortho H3 plus, it has to collide. They're able to look at its concentration and column density, and if it's lower than expected, maybe so more collisions are happening, then they're able to say, okay, this is a high density gas cloud, and if it's higher, then it's a low density gas cloud. While the pathways are not, yes.
Can you go back one slide real quick? So, in this slide, you're saying that H3 plus doesn't depend on hydrogen at all, so that's the claim. So if it's zero order, what do you actually, or what is it actually dependent on? What?
So in dense clouds, in the center of these dense clouds, you get a lot less radiation that's able to disrupt this from forming or destroy it through other processes. So it's believed to be like safer in these dense clouds, whereas there's a lot more like X-rays and UV that's in the more diffuse clouds that would get rid of. I think if I recall it correctly, I'll double check.
In terms of the formation, I think it's also partially dependent. It's also, I think, proposed to be dependent on the the photon flux through the cosmic ray flux through the cloud.
Mm-hmm. And then and something else that's important is the proton affinity for molecular hydrogen is really low, and so I mean, like in a low energy collision with H3 plus and molecular hydrogen, it's not likely to do anything. Whereas a low energy collision with CO or any other like heavier atom that's has a higher proton affinity, it would destroy this triatomic hydrogen quicker. Whereas, molecular hydrogen won't. So this is microwave picture of the center of the galaxy. They call it the central molecular zone, or if you see like CMZ, it's a pretty picture. Next slide. And
so the red is the actual spectrum, and the big picture is an artist rendition, or what?
So yeah, this is the Mustang 2 microwave picture spectrum of the center, and then this is a background probably from, they have artists in NASA that are actually really good at making, that's where all the fake news, like fake, like Earth is flat, like, so they have artists that like develop these and they just like lay over a bunch of different images on top of each other.
And then the clouds you're referring to? Clouds of what?
So these clouds, if you go to the next slide, so in these interstellar regions, you're going to have these gas clouds, and so this is the center. This is where our black hole is, and so in between these stars at the kind of this like rim right here, so outside of this like primary center, we have there's a majority, a lot of mass of the universe is in these gas clouds, and it's primarily molecular hydrogen. And there are other metals that are present as well, but molecular hydrogen is most of it. Or near these stars, I think helium's less. It's less than a sixth the ratio, so it's a good amount of helium, but mostly hydrogen.
And then the trace metals that can drive cooling in these interstellar gas clouds are like lithium and beryllium, and then like carbon monoxide and like other carbons and oxygens and stuff like that.
Yeah, and then this is a bad image, but I'll point them out. So here there are these like crosses. This is where they've detected H3 plus.
How long is the parsec again?
Parsec?
Or like what's the distance scale on this? Like how big is our solar system, for example?
I think. What's that?
I just made the Star Wars joke. I don't know if the car's actually seen Star Wars.
Yeah.
I've seen 3, 4, 5, 6.
It's so our distance, like here to there. I want to say it's in between 1,000 parsecs and 10,000 parsecs. I'll look it up though. Should be. Yeah, and so.
Wait, how are they even detecting it then at that point? Is this from like a satellite or like a rocket?
Very large
Probe?
Yeah, so this is from this is VLA, and it's like a fancy, or I wouldn't say it's new, but it's like a big infrared array, and
Land-based?
yes.
When did you get into astrochemistry? It's pretty-
You get all these cool buzzwords like dark matter halos.
You just sit at a telescope.
Yeah, and then
Center of the astrophysicist and find everything.
It's like what atmospheric chemists do.
What
They
is
just go
that?
outside and they go.
yeah, and then not an immediate challenge for the astrochemistry field, but in the near future. So they have like in the 80s and the 90s and the early 2000s, they were able to like get money and like funding for these like cool projects at VLA. But the infrastructure and funding isn't really going to be there in the 30s and 40s, and unless you want to go chase that
Send in
funding.
some grants and
Yes.
send in some grants. I'm sure NASA would like it.
So the prospects of astrochemistry being like a field that's like growing isn't too bright.
So this is not really related to what you guys are doing. So it's,
No, it's fun.
But why is the image off galactic center?
Yeah, so they pointed out in one of these papers, they found that this central molecular zone, it's just a huge gas that surrounds the further center of bodies like the black hole, and it's like arms and other stars that form there. So the central molecular zone that surrounds that, it has a center, but it's not. The center is not that of the black hole. It's shifted for some reason. They don't know.
How big would the solar system look on this graph? Would it be like this?
It's 10 parsecs.
Yeah, so
Our solar system is less than 8 parsecs.
Less than one?
Yeah.
So for reference, they're able to detect these H3 plus gas clouds here because in between us, so in between us and there are infrared stars behind these that allow us to detect them. So
okay.
you can't see the stars, and so they're very tiny.
Wait, maybe this is like a stupid question, but
No super.
if this was taken from a telescope, is it like a time span picture, or is it pointing out in one direction or looking out?
Yeah. So
Depends on how you see the Earth is flat.
yeah.
But then are we looking up or down?
Yeah, the infrared waves that we get from this are very tiny, so you need these large arrays, and so they can sit on the Earth or they can be in orbit, but they're taken over time, large amounts of time, and so they kind of rotate around the Earth they like work together. This is the Earth, right? It's like rotating. So like over time as it rotates, you create this like really big telescope. So it's over time, but the time we measured in it's nothing compared to like this time scale, like of things actually happening here.
The time scales were usually interesting, so like cooling and formation and like, so to give some scale, right? For the steady state of to use Kenny terms, for the steady state form of a interstellar dust cloud, we're interested in processes that occur on the scale of 10 to the 7th years and less. We're not going to be measuring, nobody on Earth right now can measure anything for 10 to the 7th years, right? So basically, if it's greater than that, we call it transient. If it's within that, we can assume steady state. So all the processes we're interested in are on that kind of time scale for right, like 10 to the 4th, 10 to the 7th. So any sort of time-based thing we do now doesn't actually see much fluctuation.
This isn't related.
So, kind of wrapping it up, right? We've looked at the existing cooling mechanism for 10 to the 4th Kelvin and below, which is the H2 based or HD based. And we know that there are some issues with it, like the collision itself is improbable, the Lyman-Werner radiation is like another open question. So we kind of seek to find another answer to how these first stars formed within these like mini halos. And we found that H3 formation exists, right? We see it in interstellar dust clouds, we see it in primordial gas-like states. So the next step, and we know that it forms from the top down as a Rydberg molecule, right? At like some n equals 40 or something, right? Like when the electron recombines. So there's a lot of energy emitted off, and because it's got these extra degrees of freedom, it can emit further more energy than a linear molecule like H2 can. So we can release all this extra energy as it returns to the ground state. So this kind of opens up a new way, like a new idea that this could be responsible for cooling these primordial gases because it gives off so much energy that this could end up being a favorable mechanism. On top of that, if H3 has formed in primordial dust clouds, we should be able to detect these lasing lines today, right? Using like hi-fi, like far IR like telescopes, right? They should be shifted really far into the IR. So if we can establish where we want to find the lasing lines from here on, and look for those and search for those in space today with some type of telescopes, we might get some new insights on how the very first stars in the universe formed.
That's everything.
Yeah, and we'd like to thank Will and Will especially for helping us a lot, Hikaru for helping us as well, and the lab as a whole for being a solid mentorship environment, a solid scientific environment.
Yeah, okay.
And we're more than happy to take any other questions.
So how are they detecting that H3 now in space?
Using IR telescopes, I believe. Either like in orbit or ground.
So they know where the line is?
Yeah,
H3
so-
plus,
yeah.
the Rydberg lines we know.
Well, when you were asking earlier, so the frequencies that you find the vibrational modes at are at for the ring breathing, it's 3200 wave number, and then the second vibrational mode has a degeneracy of so it has a frequency of 2500, and then it's doubly degenerated there, and then the third one is 2100. So they know where to look for the lines.
So it'd also be good for you guys to calculate what the redshift and frequencies would be expected to be.
That would be very interesting.
Because the universe is expanding.
Galactic redshift.
Yeah.
It could be an astrochemist.
Yeah. What happens when things are getting further apart? What happens if you're studying this?
Like, how would I know?
Yeah.
Living in
Because
Berkeley.
you took
Living
general physics.
in Berkeley, commuting to and from campus, how would I know the universe is existing?
literally sliding from 5. Yeah.
You're expanding too.
Yeah, it can, the universe can be like expand for a redshift, or if something's rotating, if it's rotating away from you, then it's redshifted.